Uh, Dear colleagues, let's start out today's talk. Our speaker is Fedor Nilov, and he will tell us about a family of conics tangent to four on a family of mm, similar conics tangent to four circles. Let's welcome.
So,
Yes,
thank you
please.
very much for this opportunity. Let's start with some basic things. For example, if we have five points in the plane in general position, then these points uniquely determine a conic passing through. Also, maybe I can use instrument in geometry. For example, if you have 5 points in the plane, then you can draw exactly one conic passing through these 5 points. Yes, maybe a hyperbola, ellipse, or parabola, or maybe it can be a pair of lines. Yes, and but there is some bad situation when we have 4 or greater points lie on the same line. Yes, for example, if you have 4 points, four collinear points, then you have infinitely many conics passing through these 5 points, because you can rotate this line. Yes, and union of these 2 lines is a conic, degenerated conic passing through these 5 points. And also, if you have 5 points on the same line, this is also a bad situation. But in other cases, you have exactly one conic passing through these 5 points in the plane. Okay, now classical Steiner problem is the following. So suppose you have not 5 points, but you have 5 conics, yes, in the plane, and you also in general position, because maybe there are some bad situations. For example, if all conics are tangent at the same point, yes, this is a bad situation in which 5, yes, 5. And for these 5 conics, we want to find all conics tangent to this conics. Yes, for the case of points, some generalization for this simple problem for 5 points. Yes.
So you start some, excuse me, you start some enumerating algebraic geometry, but can it be related to something like Gromov-Wheaton invariance, for example, or some other very popular things?
Yes, maybe, but I want to consider some geometrical problem related to this one. So maybe, but I will consider some geometrical problem. Yes, and for these five conics, initially Steiner proposed incorrect answer. He thought that there are exactly 6 to the power 5 conics tangent to these 5 conics. But in true, there are less number of conics. This is incorrect answer. And correct answer was given later. And okay, so some finite number of conics tangent to 5 given conics. Yes. In general position.
Well, of course, this should be related to our approach to grades when points move and we try to construct a group similar to G and K. So have you ever thought about some possible relations to that approach?
Maybe it will be interesting, yes, to think about it. Yes. But I don't know exactly. Okay. It will be interesting to think about it. Okay, but let me make some remark that there are also some bad situations. For example, if all conics are tangent at the same point, then there are, of course, there are infinitely many conics tangent to this 5, because every conic tangent to this line at this point is also tangent to these 5 given conics. But it is also interesting to study all bad situations, yes, in which we have infinitely many conics. But also maybe it also important to say that there is in initial statement Steiner consider also complex solutions. Yes, so maybe some conics may be complex, but there is a configuration, there is explicit construction of 5 real conics, yes, for which we have exactly this number of real solutions. Okay, but I want to consider some other problem, but related to this one. Let us consider not 5, but 4 conics. So for 4 conics in general position, we will have maybe several one-parametric families of conics tangent to these 4 given conics. Yes, and I'm interested in such configurations for which there is a family of conics for which all conics in this family are similar. It means that they all have the same eccentricity. Yes. And it is interesting that there are some examples, such examples. And let me show you. I want to start with some 2 known examples. And also in this problem, okay, maybe I can denote this conics. And it is possible that some conics may be points. Yes. So for example, if we have 4 points, yes, then we have a pencil of conics passing through these 4 points. Yes. So one parametric family of conics. And if you consider 4 arbitrary points, then it is easy to see that not all conics in this pencil are similar. Yes, for example, you have hyperbola here, and here you have some ellipse. Of course, ellipse and hyperbola are not similar.
Similar подобные are
Yes.
In which conics so in which cases are they similar?
Yes, for these 4 points, it is interesting that there is the following nice example. You can take 3 points, yes, not collinear, yes, which form a triangle, and consider orthocenter of this triangle, so intersection point of altitudes. Yes, maybe I can okay, I can make a precise figure. So I consider a triangle and intersection point of altitudes, and consider an arbitrary conic passing through these 4 points. And it is interesting that all these conics are similar hyperbolas. All these conics are equilateral hyperbolas. So it means that their asymptotes are perpendicular. Yes.
Beautiful.
Okay.
Okay.
So this example is known, and let me make a remark that so this you can take 3 arbitrary points. Yes. For example, if we denote these points by A, B, C, D, and here D is orthocenter of triangle ABC, and it is easy to see that B is orthocenter of triangle ADC, yes, and so on. So you have some symmetry here. Okay, so this is first known example. The second known example is the following. Suppose we have 2 equal yes, we have 2 equal circles. Intersection, 2 equal intersection circles. Sorry. Okay. And you consider their intersection points. Let me denote these circles by alpha, beta. And these points, 2 points, their intersection points, I'll consider these points as also as conics or circles, yes? So let me denote them by gamma and delta. Yes? And then I consider ellipses passing through these intersection points. And tangent to both circles. Since these circles are equal, this figure is symmetric with respect to midpoint of the segment, yes? So here you have central symmetry. So all these ellipses have the same center. And it is interesting to that all these ellipses are similar. So they have the same eccentricity. This theorem is theorem by Marcel Berger, yes, and it was in his book Geometry. Okay, but it was formulated in some other words. This statement. Okay, and here so here you have conics tangent to 2 circles, yes, equal circles, and tangent to or passing through 2 circles of 0 radio, yes, of 2 points, gamma and delta. Okay. Any questions? Okay. And so then let me show you some new examples. So at first, this example can be generalized. Here you can consider not equal circles, but 2 arbitrary circles. And the same will be true. So 2 circles. Yes. That have 2 common points. And you consider these ellipses. And it is interesting that all these ellipses are similar. Maybe it will be great to make some animation in future. Also, there are some other geometrical statement about this configuration. For example, you can prove that if you connect tangency points, so you draw a line passing through these tangency points, so all these lines are concurrent. So you can prove that they are passing through a fixed point. Also, you can consider a locus of centers of these ellipses, and you can prove that they lie on the same circle here. Also, it is interesting to consider locus of centers of these equilateral hyperbolas here, passing through this of these 4 points. So triangle vertices and its orthocenter. Okay. But, this is here is it is also a circle passing through midpoints of a triangle ABC here. And for this figure, you can also describe locus of centers of these ellipses. Okay, so this is first a new example, but it is similar to known example by Berger. Okay, and now I would like to show you a second, completely new example of such configuration. So this is the following example. So let me consider 2 circles, one inside another, and let me denote them by alpha and beta. And then I will consider ellipses which are doubly tangent to both these circles at real points. So maybe it will be good to make some remark about doubly tangent. Yes, tangents. So if you have some ellipse, then you have two families of circles doubly tangent to this ellipse. The first for first family, let me draw it. Sorry. Okay. So for first family, centers of the circles lie on the major axis of symmetry of this ellipse. Yes. But also there is another family of such circles, doublet tangent. So a circle and ellipse have two tangency points. Yes. There is another family of circles, doubly tangent to this ellipse, with centers lie on the minor axis of symmetry of the ellipse. Yes. So you have two families. And for our configuration, for our picture, we consider such ellipses such that center of a first circle lie on its major axis of symmetry, and second and center of second circle lie on a minor axis of symmetry of this ellipse. Yes. So it's obvious that if you connect tangency points, yes, here you have perpendicular lines. Yes. Because these lines are perpendicular to axis of symmetry. Yes. And for this picture, it is easy to see that all ellipses. Oh no, it is not easy to see, but it is true that all these ellipses, maybe just put it. All these ellipses are similar. So here, as you remember, we consider family of conics tangent to four given conics. Yes. So for this configuration, we have that two conics are two pair of conics are coincide. Yes. Yes. And they are circles. These conics are circles. And also we assume that one circle lies inside the other one. And for this configuration, we obtain a family of similar ellipses with the same eccentricity. And for in previous situation, in this case, yes, we have that two conics are circles, are intersecting circles, yes, in two points. So, and so these circles, yes, alpha and beta are circles, and gamma and delta are intersecting points of these circles. So we have two examples. I don't know if there are some other examples, but it will be interesting to construct some other examples, or maybe make a classification, yes, of all such configurations. Okay, maybe it will be a good idea to prove that here we have similar conics. Yes. Let me prove this for this example. And here there are, I have 3 proofs for this statement. Maybe I'll tell you geometrical, and also maybe it will be good to say that here we have some additional geometrical properties. Yes, here, but we are interested in our question. We are interested only in in statement that all these conics are similar. Yes, but also we can prove that here we already say that these lines connecting tangency points are concurrent. Yes. Here the same statement is true. So if I draw these lines passing through tangency points, then all these lines are concurrent at the same point. And here,
what do you mean by congruent lines? I don't understand.
They are concurrent. They are passing through the same point.
Concurrent. Yeah. Okay.
Yes, through some fixed point, and we also can describe these fixed points. Here, this point is a center of homothetia of these circles, alpha and beta. So, for example, if you draw tangent lines here, you obtain that these lines are parallel. So here, this fixed point is a homothetic center. But here, it is not a homothetic center. This is a limiting point of a pencil. So if you have two circles, yes, alpha and beta, you can consider a pencil of circles, so linear combination of circles. So you can draw some linear combination of circles, and linear combination of circles is also a circle. Yes, and for some values of these constants, you obtain a circle of 0 radius, so a point. Yes, and if you have 2 non-intersecting circles, non-intersecting circles, then you have 2 limiting points of the pencil, formed by generated by these 2 circles, alpha and beta. And this point is a limiting point. And but you have two limiting points. Yes. So for each limiting point, you have one family of similar ellipses here. So for other limiting point, you also have another family of similar ellipses. And it is interesting that also it is true that locus of foci of these ellipses, all foci of these ellipses lie on the same circle. So if you rotate this ellipse inside two circles, then foci of an ellipse are moving on some fixed circle, yes, and the circle will be concentric with circle beta. And also you can prove that centers of these ellipses also lie on the same circle. But for this figure, it is not true that foci of these ellipses lie on the same circle. But centers, for centers here, yes, this statement is true. Okay, but we want to prove only similarity, yes, only that all these ellipses are similar. Okay, to prove this statement, I first of all I would like to remind you definition of an ellipse or a conic using focus and directress. So if you have some fixed point focus and some fixed line directress, then a conic is a locus of points M such that ratio of distances from this point to focus and to this line, this ratio is constant, yes, and it is equal to eccentricity of this conic. For example, if you take epsilon is equal to 1, you obtain a parabola, yes. So here you have, for example, ellipse. Okay, and it is interesting that this definition you can consider generalization of this definition. You can take a circle instead of focus. So you can call it bifocal circle. For example, focal circle F, yes. Then consider a line D, and consider locus of points such that ratio of, so instead of distance from a point to a focus, here you consider a circle instead of a point, instead of a focus. You consider tangent distance, yes, a length of tangent segment from a point to this circle, this fixed circle. And you consider a locus of points such that this ratio is constant. And it is true that this locus is a conic and you can write here epsilon is a conic tangent to the circle, doubly tangent to the circle at the intersection points of this fixed line D and this circle. And this ratio is equal to eccentricity of this conic. So, for example, if you consider epsilon is equal to 1, so this ratio is equal to 1, you obtain a parabola, yes? So, for example, for a parabola, if you consider an arbitrary circle doubly tangent to a parabola, you obtain that, and consider an arbitrary point on a parabola, you obtain that distance from this point to the line through tangency points is equal to tangent to this circle. And for other conics, this you have constant ratio here. This property you can prove in different ways. This property, for example, maybe I can mention interesting way using Dandelin construction. So if you in case of ellipse, but it is not hard to generalize. Okay, for example, if you consider a cylinder, classical Dandelin construction is the following one. So if you have some section of a cylinder, you can consider inscribed spheres of this cylinder and move it inside the cylinder, this inscribed sphere, in such a way that at some moment this sphere is will tangent to plane of the section. So here we have some tangency point of this sphere and second plane. And the same thing for other side, yes? So you can also consider here a sphere inscribed in cylinder and tangent to the second plane at some point. And Dandelin observed that these tangency points are exactly foci of this ellipse of this section. And it is well-known construction, and it is interesting that this construction may be used for to prove generalized property. Yes, this property. How you can use it? So you here we consider situation then when spheres are tangent to this plane. But what if we move these spheres further? So we can move upper sphere down, and then you what we see at the second plane. What we see at the second plane, if we move upper sphere down. So we consider some second sphere or second plane, yes, and move upper sphere down. Then the intersection of this sphere with this fixed plane will be a circle. And if you move it, okay, maybe I can draw it again. So here we have this sphere inscribed in a cylinder, and consider these points. So we have a circle containing tangency points of the sphere and the cylinder, yes, and we obtain intersection points of this circle of tangency points and this conic and this section. And also we have a circle which is a section of this sphere by a second plane, yes. And you can see that this circle is doubly tangent to this ellipse. So if we consider this ellipse, yes, and consider and move this sphere, inscribed sphere in the cylinder, you and intersect this sphere with the plane of this section, then you obtain a family of doubly tangent circles. And in some position, these tangency points will be imaginary, yes. So if you yes, if you, so in some position these tangency points coincide, yes, here. So here you have contact of 4 order, yes, circle and then if you move it further, this sphere this sphere up not upper but down, yes, down, you obtain circles doubly tangent at this ellipse at imaginary points, and finally you obtain a point, yes. So a focus, you can consider focus as a circle of 0 radius which is doubly tangent to this ellipse, yes. So a focus is precisely 2 complex conjugate lines, yes, intersecting at a real point, which is a focus, and this complex conjugate line are tangent to this ellipse. Yes, but at imaginary points. And also, it is easy to see that these tangent lines are passing through points to these points on projective plane. Yes, circular points. Yes, and these tangency points are imaginary. And if you draw a line through these imaginary points, you obtain precisely directors of a conic. So here, in usual definition of a conic by a focus and a directress, directress is a line passing through imaginary tangency points. Yes. So this is exactly the similar to this situation. Yes. In similar way, you can prove this statement also for hyperbola, because ellipse hyperbola is not a section of a cylinder. Yes, so you can consider a cone instead of cylinder, for example. Also, there is some similar property, because here I consider a circle doubly tangent to this ellipse with center lying on major axis of symmetry, yes, of the ellipse. But for a circle from another family, as you remember, I said that we have two families of circles doubly tangent to the given ellipse. Yes. So for circle from another family, for which center lies on the second axis of symmetry, you have some similar property, but here you cannot draw a tangent line, of course, to the circle, but there is well-known definition of power of a point with respect to a circle. Yes. So if you consider an equation of a circle, in this way, okay, you can put in this equation an arbitrary point, not line on the circle, and then if you take a point outside the circle, so let me denote it by this function in x and y by for example p at xy. So p xy is equal to 0 is an equation of a circle. But if you put in this consider a value of this function at a point outside the circle, then it is equal to square of a tangent segment, yes? It is equal to t squared. And for this picture, you can make the same thing. So you consider line D through tangency points. You take an arbitrary point on the ellipse, for example, M, and consider distance from M to this line is and here so here if you can consider a square of this ratio, yes, and it will be equal to epsilon squared. But here instead of t squared, because point M lies inside the circle, you need to consider value of this function, yes, power of point M with respect to this circle. So you consider ratio of maybe would you know in this way, yes, ratio of power of this point with respect to the circle F, yes, and divided by h squared. And the statement is that this ratio is also constant, but let me denote it by in this way. But see, it is easy to see that for point inside of the circle, its power, this value, is negative. So here I need to write maybe, okay, I write minus here. And this ratio is equal to square of some other constant. This constant, it is not equal to eccentricity epsilon, but there is some relation between these constants, precisely the following one. If you if you consider an ellipse, so the following relation. The following relation. Okay, and you and this statement you can prove it also in some geometrical way, or using some calculations, okay, let me state that, let me make a remark that the same thing is true for a hyperbola. So for a hyperbola, you also have two families of circles doubly tangent to this hyperbola. So the first for first family, centers of the circles lie on the major axis of a hyperbola. let me draw the circle tangent to a hyperbola in this point. And here you have the same statement that ratio of tangent line to the circle and distance to the line connecting tangency points is also constant. It is equal to eccentricity of this hyperbola. And similar thing is true for circle from another family with center lying on the second axis of symmetry. Okay. Also, it is it will be good to mention that for classical definition of conic, you have two foci here in classical definition of a conic. Yes. So in classical definition, you have the sum of distances to a point on the ellipse, to foci of the ellipse is constant. Yes. But in this definition, you can also replace a foci by a circle's doubly tangent to this ellipse. So let me draw this figure. And for this configuration, for this figure, you can take an arbitrary point on the ellipse and consider tangent distance to these circles. Yes. Sorry. This is tangent distance to. And let me denote this tangent distance by T1 and T2. And it is true, and also let me consider these tangency points and draw lines through these points. These lines are obviously parallel. Because you have circles from the same family, so their centers lie on major. Wait, sorry. On major axis. And it is true that if you consider points between these two parallel lines, then sum of this tangent distance is constant. Between this, so on these arcs. But if you take point on remaining arcs, you need to consider difference or modulus, yes, of difference. And this also will be the same constant. The same constant. And it is interesting that here you have you have something similar because for definition of ellipse you have sum of distances. For definition of hyperbola you have modulus of difference, yes, of distances. And here on you have both situations, yes, sum and modulus of difference. It is very easy to prove it using our focal directories generalization using this property, and also you can prove a similar thing for two circles from other family. Some generalized bifocal property, yes, of conics. Okay, and let me prove that all circles in our initial all ellipses in our figure here, yes, are similar. Okay, let me denote tangency points and consider intersection point let me denote it by L. And first statement that L is limiting point of a pencil generated by these two circles. It is not hard to prove it using projective transformation. You can consider projective transformation taking these two circles to a concentric conics. So to some pair of concentric conics. And then this ellipse image of this ellipse will have a center coinciding with center to both conics. Yes. So these two conics share the same center. Yes. And ellipse doubly tangent to this concentric conics is also concentric to this conics. And it means that this line connecting tangency points here, these tangency points are also symmetric, will be symmetric. And this line is passing through the center, common center of these conics, alpha and beta. And it means that preimage of this common center will preimage of this common center. So common center of concentric conics is a limiting point of the pencil generated by this conics. Yes. So preimage of this line or of this point is also a limiting point of the pencil generated by circles alpha and beta. So L is limiting point of this pencil. And then I want to use the following geometrical property of the pencil of circles. If you consider an arbitrary three circles from the same pencil, okay, three circles from the same pencil. So third circle is linear combination of two given circles. And you consider tangent, an arbitrary point on one circle, and consider tangent distance to other two circles. And the statement is that ratio of these tangent distances is constant. Is constant if you move this point on this circle. But it is true only if these three circles lie in the same pencil. So it means that equation of third circle is linear combination of two circles. Okay, and here I can take one circle alpha, yes, or gamma, sorry, or gamma, one circle as limiting point. So limiting point is also a circle of zero radius. So this point L is equal to third circle, to circle gamma. And so I obtain that if I consider an arbitrary point on circle beta, for example, C, I have that ratio of CL, yes, is tangent. This is CL is tangent distance to circle gamma, which has zero radius, to tangent distance to circle alpha. Let me denote it by T. is constant. Yes. But here, I already said that here we have perpendicular lines. Yes, it is obvious that lines CD and BD are perpendicular. So CL is distance from C to line BD. Yes. But if you remember generalized focal directors definition property, yes, we have that ratio of tangent distance to a circle to the distance to the line. Yes, this ratio is constant and it is equal to eccentricity of the ellipse. So you obtain that this ratio is equal to inverse eccentricity. But if you consider some arbitrary another ellipse, yes, from this family, and consider some other point, tangency point C dash, yes, so you obtain the same ratio because this ratio H and T, yes, is exactly ratio of tangent distances to two circles in the same pencil. Yes. So it means that eccentricity of this ellipse is equal to eccentricity of the previous one. So they're similar. So this is a geometrical proof. And in this proof, we use that these tangency points are real. But as I already mentioned, that you can consider second family of these ellipses, such that this point L, intersection point L, is another limiting point. And for the second case, you obtain situation where you will have complex tangency points. And in such situation, you can use some algebraic form of this proof. So some similar proof. And also, it is interesting that there is another way to prove it using 3D way. So some stereometry view. So you can think you can consider the following picture. So you can take a hemisphere. Okay, you can take a hemisphere, and this circle will be. Let me. How would you know this circle? Oh, sorry. beta, yes? Okay. So here we have circle beta. Here we have circle alpha. And we can construct a cylinder intersecting this hemisphere in some curve. Here you have a symmetric picture. And then you can consider a pencil of quadrics generated by this sphere and a cylinder. And you can consider a cone in this pencil. And it is easy to see that since you have a pencil generated by sphere and cylinder of rotation, yes, cylinder of rotation, then cone, this cone in the pencil, will be also a cone of rotation. Right, circular cone. And then you can consider tangent planes to this cone. And these tangent planes to this cone will intersect initial sphere by some circles. And since this cone is a cone of rotation and its axis is perpendicular to the plane of initial circles, then angle between plane of the circle of this tangent plane and plane, let me denote this plane by pi, yes, plane of initial circles. This angle is constant, yes? So you obtain a family of circles in tangent planes of this cone, forming the same angle with plane pi. So it means that if you consider projection, so if you consider orthogonal projection of these circles onto the plane of initial circles, you obtain this family of ellipses. And all these ellipses will be similar since angle. So if you consider some circle, yes, and consider orthogonal projection of the circle onto some plane, then you can easily calculate. You obtain some ellipse, yes, and you can easily calculate its eccentricity in terms of angle between the circle and the plane of projection. So since these planes of the circle form the fixed angle with this plane pi, it means that their projections, these ellipses, will have the same eccentricity. So they're similar. And finally, I would like to make a remark that also you can consider two circles lie outside one another and consider family of hyperbolas. Family of hyperbolas doubly tangent to these two circles. And it is also true that these hyperbolas are similar. Also, there is some intermediate case when these circles are tangent to each other. And there are also two cases when we have inner tangency and inner tangency and outer tangency, and this is some kind of limiting case. And here you have also family of similar ellipses and hyperbolas, in this case, doubly tangent to these two circles. And finally, it will be interesting to find some other examples, and also maybe to find. Unfortunately, I have no time to prove the second example. Yes, of family of similar ellipses. Sorry, where is it? This family, yes. And it will be interesting to find some similar proof, because these two figures are have some common, yes. But I don't know a similar stereometric proof for the left figure, for the left example. So I think that's all. That's all that I want to tell you. Maybe any questions?
Thank you very much. Are there any questions, comments? Yeah, if not the case, let's thanks the speaker again. Thank you very much for
Thank you.
Thank you very much.